Good afternoon, everyone. Today we're going to take a look at 8.2. 8.2 is looking at the proportion for a sample. And so let's just dive in. As a reminder, 8.1, we did the sample mean. I wonder if I can zoom in on that. I bet I can. Well, something to explore for another video. So 8.1 was the sample means. 8.2, we're looking at sample proportions. And what we're trying to find really is we really want to know the true proportion for the entire population. But finding the true proportion of a population is extremely difficult. Proportion of an entire population without surveying the entire population, of course, is extremely difficult. We don't ask everyone, we really got to just guess. We can get close, and that's what the remainder of this book is about, the remainder of this course. But we can find a sample proportion. And we call it p hat. P hat. Why? Because it's a P with a little hat on it. And you know, clever, right? We're a group of smart people. And if you recall, proportions are x over n, where x is the frequency of a category or response, and n is the total sample size. And so another way of looking at x is the number of people in the sample with that trait. And n is the total sample size. So I'm going to pause here, give you a second to write this down. Don't want that. There we go. Okay, I'll let you pause and write it down. Go ahead and hit pause if you need to, and then restart up in a second. So if you look on the right, this is from this semester, and this was the question I posed. What do you think of Luke Skywalker in episode 1? Of the character of Luke Skywalker? And the categories were, he's a whiner, he's heroic. And then we put in not applicable if you didn't watch Star Wars. And we had other. Now, other was big. A bunch of responses. There was different kinds of things like he's hot and things like that. I want to eliminate those. Let's just get it down to whether or not he was heroic or not. So if you look at this distribution we have, this is a histogram or a bar graph of the responses. We had 33 people say he was a whiner. 9 people say he was heroic. If we just ignore the other 2 categories, what we have is 33 plus 9 is 42. So if my question is, what proportion of the population thinks the character of Luke Skywalker started as heroic? Luke started as heroic. We have P hat. There was 9 people out of 42. Now this is exact. Leaving it as a fraction keeps it exact, but oftentimes we want a decimal because we're trying to work with numbers, and fractions just really don't give us a lot. So 9 divided by 42. P hat is approximately 0.2142857714. I'm sure there's more decimal places. If we round to 3 decimal places or 4 decimal places, as MATLAB often likes to do, we're going to have 0.2143. Here, P hat is called a point estimate. It's a point estimate. And we call it that is because it's an estimate. This is an estimate of the proportion of the overall population that thinks Luke is heroic. Okay, we'll pause and just ponder on that for a little bit. Let you write it down. Please hit pause if you need to. Okay, I'm going to turn the page. Now, I'm going to ask this of my students next semester. How likely is it just start a new page? How likely is it that next semester students will think the same thing? Will have the same P hat. It seems pretty unlikely to me. This is highly unlikely. And where I'm going with this is P hat is different for different samples. And that means, since it changes, it's a variable, and we call it a random variable. And therefore, it has a probability distribution. You might hear chiming. I just got done posting my first video on YouTube, and I imagine that students responding and saying, yay, it was good. No, that was garbage. We'll find out. And for probability distributions, what did we have before? We have a mean. For when we're looking at proportions, we'll say mu of p hat actually equals p. And sigma p hat is the square root of p times 1 minus p over n. This is just something you're going to have to remember. Maybe flashcard it, stuff like that. Now, when we looked at the sample mean, everything went to normal distribution relatively quickly, even the uniform distribution, if you recall. But what about when we're looking at proportions? Proportions is a little bit different. So this is going to be the criteria that we're going to use for a proportion distribution. For the sampling distribution of a proportion of p hat, for it to be approximately normal, you're going to see some criteria you've seen before. And I told you it was going to come back. A, we want n times p times 1 minus p to be greater than or equal to 10. And for B, we want samples to be independent. And the way we try to meet this one is we want n to be less than 0.05 times big N, where big N is the total population size. And this is our sample size. And this 0.05, it corresponds to 5%. Our sample needs to be no bigger than 5% of the overall population. Give you a second to write those down. Then we'll just take a look at some problems. All right, I'm going to turn the page. The first problem we're going to look at is 8.2. This is going to be problem number 3 from our homework set. So let me bounce on over to it. Okay, so in my problem, it says, suppose a random sample of size n equals 75. I'll make a jot of this down, and I'll bring up what I'm writing back up in a second. N equals 75 is obtained from a population whose total size is 25,000. That's our big N. And whose population proportion with a specified characteristic is P equals 0.2. They surveyed all 25,000. They know the exact answer for the proportion. Describe the sampling distribution of P hat. If we look at the options, it's asking us if the distribution is normal. So let's go back to our camera. Recall, for our distribution to be normal, we need n times p times 1 minus p to be greater than or equal to 10. Does that work here? N is 75. P is 0.2. 1 minus p is 1 minus 0.2. This is 75 times 0.2 times 0.8. And if we pull out a calculator, just a good old calculator, I get 12. How does that compare to 10? Which is larger? Well, the 12 is, so the alligator mouth goes after 12. 12 is greater than or equal to 10. It satisfies the first criteria. The second criteria we wanted to check was, is n less than or equal to 0.05 times big N? So this is the question, is 75 less than or equal to 0.05 times 25,000? We enter this into our calculator. Make sure you put enough zeros in. 0.05 times 25,000 is 1,250. Which one of these is larger? The 1250 is larger, so 75 is less than 1250. This gives us the samples are independent. Or should be, if we do enough samples like that. There's no reason to think we're going to have a big overlap. And so we meet both of the criteria. That means this is going to have approximately a normal distribution when we look at a probability distribution. So let's bring that question back up and answer that. There's two answers that say approximately normal. They both say n is less than 0.05 big N. The only difference here is n times p times 1 minus p. Is it less than 10 or is it greater than or equal to 10? It was greater than or equal to 10. For me, that's option D. So I'm going to choose option D, and there we go. Part B. Not even part B. This is still part A. Part A. Determine the mean, and I'm going to guess they're going to want p hat, or the standard distribution as well. But let's take a look at what we're doing. We'll do them one at a time. So what was p hat or mu? Remember, if you we'll go back to your old lecture notes, last page, we had mu was equal to p. Mu of p hat equals p, which is 0.2. Sigma of p hat was p times 1 minus p over n, and we take the square root. I already calculated 1 minus p. That was right here. So I'm going to use that down below. 0.2 times 0.8 over 75. And then we take the square root. Now, it's possible to do these all at once. I find it easier to use the answer button. So I'm going to do 0.2 times 0.8 equals. Then I'm going to tell it answer divided by n, which was 75. And then I'm going to say, take the square root of my answer. And this gives me, I don't know how many decimal places StatCrunch is going to want, 0.046188021. Now, you can do this all at once, but you're going to have to use parentheses, and it can be a pain in the butt. So I'm going to say square root, parentheses. I'm going to give it another parentheses and do the 0.8 times 0.2 on top in my first set of parentheses. Then I'll divide by 75 and I'll end the parentheses. If you look, I've got 2 ending parentheses, 2 starting parentheses. It's a little tricky doing this. I think it's easier to do it the other way, but it comes up with the same answer if you enter it correctly. Okay, so let's see what they asked us. We have that. That was just p hat, which was 0.2. And it want, oh, look at that, 6 decimal places. Wowzers. 0.046188. And I look at the next decimal, it's a 0. So we're good there. That's 6 decimal places. What is the probability of obtaining x equals 21 or more individuals? That is, what is probability p hat is greater than or equal to 0.28? So I'm going to switch over to my camera. I'm going to keep sigma and mu up while I work here. And I'm going to jot down what they're saying. Probability that x is greater than or equal to 21, that's 21 or more. And this is saying, or probability p hat is greater than or equal to 0.28. Where did they get that 0.28? They gave us 21. Where did the 0.28 come from? Well, remember p hat is x over n. So we're looking at 21, which is the x they're talking about, over 75. And if we do 21 divided by 75, we get 0.28. That's where they came up with that. So a lot of times when you're doing these problems and you're working with proportion, you're going to want to take your actual frequency, the number of people that said the response, and convert it to a proportion of your sample. Okay, that way we can compare it with the other p's we're looking at. So how do we calculate this? Well, here we can go into StatCrunch. Let me open up a new one. There we go. We're going to go stats, calculators, normal. Okay. We have our mean. We calculated the mean and standard deviation right here. So I'm going to enter those in. And I'm going to use the number of decimal places they specified, which was 6. I want the probability that x is greater than or equal to that 21, which was 0.28. I click compute. I don't know how many answers they're going to ask for. So the probability that p hat is greater than or equal to 0.28 is 0.04163219. We can't make this calculator right here. I can't make this calculator right here say p hat, but as soon as we convert the mean and standard deviation to reflect being proportion, then you can, in your head, just convince yourself x is represented as p hat. That's going to be what you're going to have to do. Okay? Let's come back here and take a look at it. 4 decimal places. I had 0.04163. 3 I would round down, so that's going to be my answer. Continue. What is the probability of obtaining x equals 12 or fewer? Well, my mean hasn't changed. My standard deviation hasn't changed. They just want me to change this to 0.16. So I'm going to switch back to the camera and write this down, because I will take pictures of these notes and upload them so you can have them next to you while you watch the video. Part C said probability that x was less than or equal to 12. Fewer than is less than. And how did they come up with the 16? They took that 12 and they put it over 75, the R old N. And 12 divided by 75 should give us 0.16. It does indeed. 0.16. So this turns into the probability p hat is less than 0.16. We keep mu at 0.2. We keep, standard deviation was 0.046188. Nothing's changed. All that's changed here is our result. Our result, and I'm going to imagine they want 4 decimal places as well, 0.1932. I can take a check, look at it. I'll pause and leave this up for a second if you need it up longer though. Okay, let's take a look at it. 4 decimal places indeed, 0.1932. That was it for question 3. We're also going to look at question 4. So question 4, what do we have here? According to a study conducted by a statistical organization, the proportion of people who are satisfied with the way things are going in their lives is 0.74. I suspect that isn't the case today, not with everyone being in a shelter in place. But in general, let's just take a look at it. 8.2, number 4. What does that mean? What is that 0.74? 0.74 is they're telling us what the proportion of the population is. This is our main P. P is 0.74. And then they say, suppose that a random sample of 100 people is obtained. We're going to use n equals 100. Now, I jotted those down. Let's just read through these things and if I can figure out what they're trying to say. Part A is, suppose the random sample of 100 people is asked, are you satisfied with the way things are going in your life? Is this response to the question qualitative or quantitative? Explain. Qualitative could be any answer. Quantitative was a number. Qualitative can be a number, but it's usually not, but it can be. Quantitative is always a number. What are the possible answers to are you satisfied with the way things are going in your life? Yes, no, I'm not sure. Kind of. I mean, you can get some vague answers, but you can usually break it down to yes or no. None of those are numbers. Since they're not numbers, the response is qualitative. Now let's look at our answers here. For me, A says the response is quantitative, that's out. B says the response is qualitative because the responses can be classified based on the characteristic of being satisfied or not. That sounds right, but let's check the rest. I like B so far. I'm going to click it. C, the response is quantitative because the number of people satisfied can be counted. Well, no, that's not really what the response is. The response is yes or no. The number of people satisfying can be counted, but that doesn't make the response quantitative. The response is qualitative because the number of people satisfied can be counted. Again, it just doesn't have anything to do with whether you can count them. It's what their response is. So I feel very confident in saying B. Explain why the sample proportion p hat is a random variable. What is the source of the variability? This is just a lot of critical reading right here. So A, what do we know about p hat? Let's just think about what we know about p hat before we start reading them. So p hat is the proportion in the sample that responded, let's say they're satisfied. I can ask 100 students this semester if they're satisfied, and I can ask a different 100 students last semester if they're satisfied. And I might have the same proportion, but I suspect it won't be. Oftentimes because n is going to be a different size, and therefore it's really hard to come up with the exact same proportion. But that's pretty much what's going on with p hat. So let's see what's going on here. Response A, the sample proportion p hat is a random variable because the value of p hat varies from sample to sample. This is true. The variability is due to the fact that people may not be responding to the question truthfully. Well, that's possible, but why would people lie? Why would you lie about it? I'm going to guess that's not the one, but let's put it back on the back burner. It might be. Let's take a look at B. The sample proportion p hat is a random variable because the value of p hat varies from sample to sample. Again, that's true. The variability is due to the fact that different people feel differently regarding their satisfaction. That's definitely true. Each of us feel differently. I'm feeling very, very good about B, but I'm going to take a look at C and D. The sample proportion p hat is a random variable because the value of p hat represents a random person included in the sample. That's not what p hat represents at all. P hat represents the frequency over the total sample size of the people that responded that way, and it wasn't or not whether or not it was truthfully. C is out. D says the same thing. P hat represents a random person. It does not. It represents a group of people. So B is what we're going to go with. Might be different on yours. All right, so describe the sampling distribution of p hat. This is where they're going to ask us, do we meet the criteria? So let's look at the criteria. Notice up above, we've got P is 0.74, N is 100. Let's calculate our stuff. So we want N times P times 1 minus P to be greater than or equal to 10. 100 times 0.74 times 1 minus 0.74. Well, this is 100 times 0.74 times 0.26. And I'm going to need that later. This is 1 minus P. Let's figure out what this is. 100 times 0.74 times 0.26 equals 19.24. How does that compare to 10? 19.24 is almost double 10. So yes, it meets that criteria. The other criteria we wanted n to be less than 0.05 of the total sample size. Well, let's come back and look. Did they give us a total, or not total sample size, total proportion, or total population size? They don't. But even if we just looked at the population of a school, the population of a city, a state, everything's going to have an n much, much bigger than 100. 100 is usually, let me put it on the camera. 100 is usually a lot less than n. And we will assume so here. Pause and let you write that down. Okay, let's take a look at what we got. Since the sample size is no more than 5% of the population, it's less than, so that which is the opposite of no more than. And n times p times 1 minus p, we actually calculated it, 19.24. It's greater than or equal to 10. The distribution of p hat is approximately normal. They want mean and standard deviation. We're going to have to calculate this real quick. Okay, so let's go back to our camera. They want mean and standard deviation. Well, what was mean of a p hat? This is actually equal to p, which was 0.74. Standard deviation was p times 1 minus p over n, and we take the square root. (0.74). We did the 0.26 up here. That was 1 minus p over 100. Last time they wanted 6 decimal places, so I'm going to write down everything. Divided by 100. And I'm going to take a square root of my answer. And I get, this is everything my calculator reveals. Your calculator might show more or less. Hopefully it shows 6 decimal places, or you need to get a new calculator, because that means that thing's archaic. Those are what they wanted. Let's go back and answer the question. Pause for a second to let you write it down. Okay. Oh, it wanted 3 decimal places, so a small number this time. Don't you love how they change it up on you? My sigma was 0.0438. 43 is the 3 decimal places, and 8 would mean I need to round that 3 up to a 4. So I'm going to go back and make that a 4. Excellent, 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 excellent. In the sample obtained in part A, what is the probability that the proportion who are satisfied with the way things are going in their life exceeds 0.77? What does that mean? So, camera. What they're saying is, what is the probability p hat is greater than 0.77? Well, we have our mean here. Here's our mean. Here's our standard deviation. Let's plug those in and see what we come up with into our normal calculator. Remember, it's stats, calculator, normal. We're going to replace the standard values with our new values. They use 3 decimal places, so we'll use 3 decimal places. And let's just check their wording again. Exceeds 0.77. Exceeds is greater than, it's higher than. And I want to make this bigger than. And they give me a value. It says to 4 decimal places. What do I have here? 0.24767 would be the 5th decimal place. I only want 4 decimal places, so I'm going to go back. 7 is bigger than 5. I'm going to round that 6 up to a 7. And I'm going to make a note in my notes that this was 0.2477. Okay. Using this information from C was where we calculated the mean and standard deviation. So what they're saying is keep the same mean and standard deviation we just used. Would it be unusual for a survey of 100 people to reveal that 66 or fewer in the sample are satisfied? What does that mean? 66 or fewer, they're asking for the probability that X is less than or equal to 66. We don't want to work with X though. We want to work with P. How does that translate? There were 100 people in the sample, so P hat is 66 over 100, which is 0.66. What I'm looking for is the probability that, big P on the outside, P hat is less than 0.66, using the same mean and same standard deviation we did in the last problem. So let's do that. And I get 0.03451817. I don't know how many they wanted. Can't hurt to write them all down, and then when I'm checking it, let me leave that up there a little bit longer for you though. Okay. The probability that 66 or fewer people in the sample was satisfied, round to 4 decimal places. I had 0.03451. 1 is the 5th decimal place. It's below 5. I'm going to round down. So I've got 0.0345. What's the rest of this question asking me? They're asking me if it's unusual. What was the requirement for unusualness? If you recall, unusual things were less than 0.05. Let's go back to the camera. Is this unusual? What we're asking is 0.0345. Is that less than or equal to 0.05? Yes, it is. Now, I noticed something before I clicked over. I'm going to click back to it real quick. It is unusual because the probability is less than, and notice then I have 0.05 as an answer, but they were sneaky and threw in a percentage symbol. 0.05 is not the percentage, it's the proportion. If we want to see what that is as a percentage, multiply it by 100. and it becomes 5%. So many of you, if you don't watch this video, are going to get frustrated on that problem because you're not going to see that percentage symbol. And it's just a single symbol, and it changes the whole meaning of the answer. But we've got a probability of 0.0345, which makes it unusual because it's less than 5%. All right, so that's actually 2 of the 6 problems. I will let you guys work on the rest. As a quick recap, let's do our recap page. A recap for sample proportions. The requirements for approximately normal. We want n times p times 1 minus p to be greater than or equal to 10. We want our sample size to be less than 5% of the population. If we have that, our mean is just p, and our standard deviation is the square root of p times 1 minus p over n. We can use this in StatCrunch, stats, calculators, normal, enter in these 2, and p of x less than or so-and-so, must turn into p of p hat less than or equal to, or we can have the greater than or equal to symbol, but you got to convert it to p hat. And the way we convert it to p hat is x over n. I hope that helps you guys. I will be doing more videos soon. This was a CloudServe based Zoom, so it should upload automatically, and I should be able to upload it to our Canvas accounts relatively quickly. I will also download it and translate it into a YouTube video because I like having a YouTube video channel. I think that's kind of neat. Peace.